conclude the discussion on droplets on smooth flat surfaces by looking at the shape of a puddle. By puddle, I mean it's a, uh, it's a droplet which is very, very large compared to the capillary length. As you may recall, the capillary length is the length scale where surface tension and gravity become comparable to each other. So if you consider droplets which are much smaller than the capillary length, then the droplets assume a more spherical shape and you can treat it part of a sphere. We had actually done a spherical cap. In the spherical cap limit, we had actually done a variational problem. And if the droplets become much larger than the capillary length, then gravity becomes important, and gravity tends to flatten the upper surface of the droplets, as shown on the right figure. Now, what we want to do is to ask a variety of interesting questions on this simple problem. What is the radial extent to which a puddle spreads? What is the thickness of this puddle or the height of the liquid on the puddle? What is the shape of the interface very close to the contact line? Now, also notice in the figure that I've shown droplets of different volumes but having the same contact angle theta e. If you may recall, in the last lecture, we said when we derived the Young's equation, we found that the Young's equation is applicable very close to the contact line. And that's a length scale where gravity is anyway not very important. Surface tension forces are the most important. Or in other words, the contact angle is primarily determined by the various surface energies that are present in the problem. And if you're in an equilibrium situation, then the surface energies by themselves do not depend on the volume of the droplet, and therefore it is not surprising that we can have droplets of different sizes yet having the same contact angle at the wall. So let us begin the analysis by first writing down key questions that are of interest to us, and then we will take it up, we'll do the analysis for a large puddle. If you may recall, we had defined the capillary length L, C, which is defined as the square root of gamma by delta rho g, or this is approximately gamma by rho g, typically because the density of the gas is so small compared to the density of a liquid. So in this case, the radius of the droplet is much smaller than the capillary length, and in the other limit, radius is much larger than the capillary length. And when this happens, the upper surface of the droplet basically tends to flatten out, and this flattening will leads to a constant thickness, which we'll call it as H infinity. H infinity is the thickness of the droplet far away from the contact line. Okay, and let's basically define a few important things. Rather, let me maybe first state the important questions. The key questions are: what is the radius of the puddle? Another question could be: what is the height H infinity that's shown on the screen? You could also ask, what is the shape of the drop near the contact line? Okay. Now, to do this analysis, I have considered a simple schematic here of a puddle. I am only showing one side of the puddle because the puddle essentially becomes flat as you go far away from the contact line. Now, we will define a few key terms here. So we make another sketch of the interface, and with respect to the horizontal, at any point, so I'm trying to make a sketch of a portion of the interface on this puddle. At any given location, I could have defined a local angle theta. This local angle theta is the angle that the interface makes with the horizontal. So I could define a small triangle here, And if I say ds is along the interface, dx is taken along the horizontal, and dh is taken along the vertical, where the interface height at any given location, interface position, is given by y is h of x, where x is around the horizontal coordinate and y is my vertical coordinate, right? So if I were to do this, then I have cosine of theta would be dx by ds, sine of theta would be dh by ds, and tan of theta would be dh by dx, which we can just call it as hx. We can further also write cosine of theta as 1 by square root of 1 plus hx square. We have seen this a few times. Now we will use some of these results, some of these relations. Now let's consider a large puddle on this. And what we want to do now is to consider a material volume. So let's consider a material volume or a control volume, which basically extends all the way from the contact line and ends at a portion where the puddle has become basically flat. So this is the angle here is theta e, and the control volume that's of interest to us, maybe you should also mention that the height is h of x, and the control volume that's of interest to us is this portion. This is my control volume, and we look at what are the forces that are present on this control volume. Let's show the forces. Again, I'll show the forces in green. So we have a surface tension force here. This is gamma. Here on this control volume, we have also a solid liquid surface tension force, gamma SL, because this entire region is covered by the liquid. And on the other side, I have solid, gamma solid. You can also call it solid vapor if you want, but solid. Are there any other forces present in the problem? Yes, we are considering a situation where gravity is important. So gravity is downwards. And as gravity is important, then the pressure across the thickness of the puddle will vary. So in other words, there is also a gravitational force, hydrostatic pressure, and this hydrostatic pressure is just acting this way. This is P. This is the hydrostatic pressure. Now what is the shape of this hydrostatic pressure? If I were to extend this drawing here, then the hydrostatic pressure would be something like this. You would have so the hydrostatic pressure is the greatest at the bottom, and as you go towards the top, the pressure will become equal to the atmospheric pressure above. Okay, so this difference in pressure will act on this control volume. So let's write down each of them. Okay, let's write down the force balance. On the material volume in the horizontal direction. By the way, this is P, which is a function of y. Okay, let's write down this force balance. So we have the forces are surface forces. What are the forces, surface forces? Now if you see the surface with the directions that I have written, it is just gamma solid that's acting on the left, and on the right we have, or rather let me just respect the directions that I've written. So we have gamma solid, gamma surface tension plus gamma solid liquid minus gamma S. Note that there is no contact angle in this because I'm writing it for a control volume that is extending all the way from the contact line to the region where it has become, the upper surface has become horizontal. And when the upper surface has become horizontal, the surface tension force gamma also becomes horizontal. This is surface forces. And we have hydrostatic pressure. This is integrated over the thickness of the liquid. And what is this hydrostatic force? This we'll call it as P, and this quantity P essentially goes from 0 to H infinity rho G times H infinity minus Y dy, right? So if you notice here, when Y equals H infinity, when you're at the very top, the pressure goes to 0, because I've basically, I'm only interested in the difference in the pressure. So the pressure of the above the atmosphere only adds a constant value which can be ignored. But if you basically go to the very bottom, the pressure at the bottom, that is on the solid surface, will be rho G H infinity. So now I have to integrate this going from the bottom to the top, and this essentially gives me half rho G H infinity square, correct? And so what I now have is, I have gamma plus gamma solid liquid minus gamma S, that's the thing, minus gamma S, minus half rho G H infinity square will be 0. This is what I have, and therefore I simply get, if I use the Young's law, the Young's law says there is a relationship between the different contact angles. What is the relationship between the contact angles? If I look at a force balance near the contact line, I have gamma this way, theta E, this is gamma solid liquid, and this is gamma solid. Then I simply have gamma solid minus gamma solid liquid minus gamma cos theta E is 0, and therefore I simply have gamma SL minus gamma S will simply be gamma minus gamma cos theta E, right? And if I substitute this result into the above relationship that we had got, we simply have gamma minus gamma cos theta E is equal to half rho G H infinity square, and therefore I have H infinity square will be 2 by rho G into gamma into 1 minus cos theta E, or this is nothing but H infinity square will be 2 LC square 1 minus cos theta E, or in other words H infinity is square root of 2 LC into 1 minus cosine of theta E. That's the height of the puddle. Height of the drop of or height of the drop or puddle. Now note that we have basically done this analysis only for a large puddle where my control volume is very large. If on the other hand my control volume was small, if I were to take a smaller control volume, then I have a analysis near the contact line. The idea is the same. I have my coordinate system x and y. I have an interface here, and now the forces are as follows. This is gamma, and at this location the local angle is, let's say, theta. My control volume of interest is this one, and again I have the same idea. The pressure varies linearly. This is the pressure, and at this height the local height is y equals h of x. It is varying as a function of x, and therefore if I were to do a control or horizontal force balance on such a wall, on such a puddle, on such a droplet, then we have gamma cos theta plus we have gamma solid liquid and we have gamma solid, gamma cos theta plus gamma solid liquid minus gamma solid, and then I have minus 0 to h rho g into h minus y d by, this will be 0, and if I do the simplification I simply get gamma cos theta plus solid liquid minus gamma s is rho g h square by 2. Okay, then using the contact angle theta e, just like what we had done earlier, we get gamma times cos theta minus cosine of theta e will be rho g h square by 2. Okay, this is what we have. Now we had already derived an expression for cosine of theta. Cosine of theta was 1 by square root of 1 plus hx square, and therefore I have cosine of theta minus cosine of theta e is half rho g by gamma h square, or this can be rewritten as cosine of theta is equal to half h square by lc square plus cosine of theta e, and therefore I will now have 1 by square root of 1 plus hx square is equal to half h square by lc square plus cosine of theta e. That's a shape, that's the equation. This is governing equation for the shape of a puddle near the contact line. Okay, so you can again convince yourself that when h goes to 0, that is as you approach the contact line, the first term on the right hand side goes to 0, and therefore you recover the cosine of the angle would just be equal to the local slope near the contact line. Okay, so we've got the height of the puddle, we've got the local shape of the puddle. What else can we do? We can actually do a simple analysis on this problem. We can look at the cases where the angles are very large or very small. Okay, let's quickly do that. So So for a large drop, we already found that h infinity that we got was root 2 LC into 1 minus cosine of theta e, correct? Since cosine of theta e is 1 minus 2 sine square of theta e by 2, this will be square root of half. Did I move? Oh, I forgot this half here. Please correct that. This should be square root of half. Please add the square root there. I just forgot to take the square root of that quantity. Therefore, I can now have 1 minus cosine of theta e is just 2 sine square of theta e by 2, and therefore h infinity now becomes 2 LC sine of theta e by 2, right? So if theta e is much smaller than 1, then we have sine of theta is approximately theta, and I simply have h infinity is approximately LC times the local angle. So it just says that the local height would depend on the capital length and the angle there. Okay. So in such a case, the height of the puddle, even far away from the contact line, depends on the equilibrium contact angle. Okay, this is true for drop slits which are very which make a very narrow angle close to they're for very hydrophilic surfaces. Okay, now what about the radial extent? The radial extent of the puddle. So let's consider you've dropped a puddle, or you've created a puddle on the surface, and the puddle approximately takes a nearly circular shape, and the goal is we want to find out what is the radius of this puddle, right? So for a large puddle, volume V, let's call this volume that you have poured here, is approximately equal to the thickness of a disc. So if I see from the top view, I see a circle, but if I see from the side view, what we see is some kind of a disc, right? And the disc is nothing but the volume of the disc is pi r square times h infinity. H infinity is the thickness of the disc, and r is the radial extent of the disc. Okay. Now this can immediately, we can get the volume to be pi r square times 2 LC into sine of theta e by 2, and therefore I have the radius square is the volume divided by 2 LC pi sine of theta e by 2, or in other words, the radius of the puddle would be volume divided by 2 pi LC sine of theta e by 2. This is the volume of the puddle. Now you can do a simple experiment. A simple home experiment would be you make a plot of R versus V. So V is something that you input and R is something that you measure, and you do this carefully, and what you see is that if you don't change the surfaces, the contact angle will not change. The capillary length will be determined by the liquid. Typically you will take water. The R goes like V power half. So if you were to pour water, now what you should do is you should, in the log scale, you should get a V power half. This is in the log plot. If you do a log plot, the slope should be half. So you can test this to see how good is the prediction that we've got using this very simple static analysis that we have done. Okay. So in this lecture we have seen the shape of the puddle. We have determined the radial extent of the puddle. This concludes the discussion on droplets on smooth surfaces. There are a few more things that I want to cover. We want to look at what happens if the surface is not perfectly smooth. The surface in most cases is undulating. So there are some well-known simple models to determine the effective contact angle for such a surface. Note that thermodynamically, when we apply equilibrium, the contact angle is still given by the Young's angle, but that's not the angle that we may detect macroscopically when we do an experiment on a rough surface, and that's because the microscopic angle, even though it may be the true angle near the contact line, the angle that we actually detect in an experiment is an apparent angle. That's the angle that is visible to our naked eye and or to a camera, and we want some simple relationship between this apparent angle and the microscopic equilibrium angle, the Young's angle, in terms of the roughness as well. What is the nature of the roughness? What is the interaction between the liquid droplet and the surface? What kind of a configuration that the droplet takes on the surface will also determine this apparent angle. Those are the kinds of questions that we'll be looking at soon. Thank you. See you in the next lecture.